something. And so I was like, okay, how about at the very end, for those that really want to stay, we'll do a quick talk. And the thing that's been kind of irking me for a while is SIBO, right? So our talk will be focused on SIBO. Now, so many of you obviously see patients. How many of you, by a show of hands, get super excited when it's a SIBO patient, right? You're like, yes, this is so easy and amazing. I love it, right? And this patient's not at all going to be pissed and not at all going to be irritable. It's so simple. It's not. SIBO is a big pain in the butt or the stomach. And the whole idea behind this talk is going beyond the bloat, because I work with a lot of practitioners. Obviously, I don't see patients, but I work with a lot of practitioners, and the question I get quite often is, what is going on in the gut when it comes to SIBO? There's a lot of different theories. This is certainly not going to be all the answers, but what I want to do with this quick talk is kind of stoke some thinking and ideas in this group, right? And kind of bring about some connections that maybe you're not aware of with regards to SIBO, which will actually help give us a more comprehensive view on how we should be looking at this particular condition. For the most part, your patients are being bothered by this really dysfunctional bloating and distension of their gut, right? Whether the bloating and distension is truly in the small bowel, or is it in the stomach, or is it part of the large intestine, we don't really know, but it's just sticking out, right? And that is a huge quality of life issue. I see pictures online all the time of people that have 90-pound frames and bellies out to here, right, from just eating something. I also get a lot of people saying, my SIBO's really bad. And I go, okay, can you tell me a little bit about how you experience it? And they go, the moment I bite for my first bite of food, my gut just goes out like that. And I'm like, well, that doesn't quite make sense, right? If SIBO is overgrowth of fermenting bacteria in your small bowel, especially in your distal small bowel, then how is it that the very first bite of food races there quickly at the speed of light, gets fermented, and gas gets produced, right? There's something else going on, right? There's stuff in the stomach probably going on. There's other dysfunctions that are likely tied to it. And at the end of the day, it's SIBO, the bloating and the distension. Is that the biggest concern we should have, or should we be looking at other underlying things that SIBO, that bloating and distension, seems to be telling us, right? So that's the idea behind this. And again, this is to stoke some conversation. It's not going to be a very long talk. I'm sure many of you have suffered through long talks of mine, but I promise you this won't be. So let's talk a little bit about SIBO, which also kind of overlaps with IBS, both IBS-C and IBS-D. And I love that we have all these distinctions, but really, it's all the same thing, right? Everything is irritated. Nothing's really working right. Between 4 and 78% of irritable bowel syndrome, IBS, is caused by SIBO. Don't you love science like that, right? 4 or 78. So it's somewhere in there, right? I mean, what sense does that make? Maybe they're the same thing, but let's look a little further. Most common symptoms of IBS, both C and D, are abdominal pain, discomfort, irregular stool, form and passage, bloating, constipation, either hard or lumpy, or diarrhea, depending on whether you're C or D, or you're mixed between the two, which a lot of people are. And the most common symptoms of SIBO are abdominal pain, discomfort, bloating, flatulence, loose motion, constipation, so on. There's so many similarities. So we're, as we're trying to deal with this condition, we're trying to put labels on it and trying to figure out, okay, I am actually methane-based SIBO. I am hydrogen SIBO. What do I do about hydrogen SIBO? What do I do about methane SIBO? Oh, I'm not SIBO, I'm IBS, right? At the end of the day, I think it's like a whole series of dysfunctions that are leading to the symptomologies that people feel. And when you dig a little bit in the research, you find that it's really the canary in the coal mine talking about a much bigger potential problem in these particular individuals. We also know that SIBO is defined officially as an increase of bacteria greater than 10 to the 5 colony-forming units per mil. That's if you do the aspirate, right? If you actually do the aspirate from the small intestine. There is a hydrogen breath test and the other breath tests, 2 different forms of them. From what I hear, it's about maybe 50% accurate. It's hard to tell. I know a lot of practitioners use it, get false negatives and so on. But the aspirate test is really the kind of the gold standard on this. And it's widely accepted that stasis is a fundamental part of SIBO, right? Stasis meaning the bowel's not really moving. And we'll talk about that a little bit as well. Here are the questions that I had when I started looking at SIBO. And then people started talking to me about it. And part of this is, I went to the UK, I get to lecture in different parts of the world, which is really kind of a treat. And in the UK, they're just now starting to talk about this, right? I remember 3 or 4 years ago being at the Integrative Medicine show there, asking people, do you guys deal with SIBO? And they're like, we don't know a SIBO. What is a SIBO? They said it, of course, in a much more elegant way with their accents. But they're like, we don't know what SIBO is. This trip, we were just there a few weeks ago, there's tons of questions about SIBO, right? So it's crossing the pond. And in that time, I started thinking about what is SIBO, really, right? So the questions that came up in my mind is, what is overgrowing? What is it actually? And then are they dysbiotic bacteria or are they native to that environment? Right? So are they coming from somewhere else and they shouldn't be there at all? Or are they the normal microbes that are there, usually at 10 to the 2, 10 to the 3 CFUs, and now they're a couple logs higher because of some variable? Right? So that's a bit important question. And if they are dysbiotic, meaning they're coming from somewhere else, where are they coming from? Now, the most common explanation I've heard, and I've heard this for the last 7 years, is they're coming from the bottom up. Right? There's some sort of dysfunction in the ileocecal valve. Cecum bacteria are moving up because of various pressures, and they're making their way into the small bowel. I think that's probably part of it. And I'll show you some information that seems to say, okay, that could be part of it. But that is a really unique dysfunction, right? Because the other question is, why are they overgrowing? Right? This seems to be so common. This is such a common condition that something like an ileocecal valve dysfunction doesn't seem common enough to match the commonality of SIBO, and certainly not IBS, right? So maybe something else is going on. What is driving the stasis? I think everybody can agree stasis is part of it, right? The bowels are stopped or they're slowed down to a certain degree. There's a couple of different ways of the bowels moving. But what is driving that stasis? And then what are our natural protections against this issue? That's the question that I always ask, right? I always go back to like some sort of evolutionary biology. Like I said, when I grow up, I want to be like a lot of people in this room, including Rob. He uses that evolutionary biology mindset. The idea is, what do we have naturally that's happening in our gut that protects us from all of these problems? So my thinking is it has to be multifactorial. Right? So it's not just some sort of aberrant growth because of diet, only, or some dysfunction in a valve. There's got to be something else happening. And these must be driven by common behaviors. This condition is far too common for it to be some sort of, elusive, uncommon dysfunction, whether it's genetics or physiology or behavior. It's got to be driven by common stuff. So that's kind of how I was thinking about it. And then I'm just going to share with you my thoughts on what I've found on this to answer these questions. And then based on that, I'll tell you what I think should be happening with SIBO in terms of treatment. And then, of course, you can tell me if I'm crazy. So to answer the first couple questions, what is overgrowing and are they dysbiotic and native microbes? So digging into this a little bit, there's some really great clues on what is happening in SIBO in certain conditions where SIBO is really prevalent. Right? One of those types of conditions are liver failure conditions, right? Non-alcoholic fatty liver disease, NASH, steatosis, all of these have SIBO as a major feature of those conditions. So in studying these conditions, they tend to find that the predominant microbes in a healthy small intestine are things like Blauschia, Rumnococca, and then overgrowth is characterized by actually a bit of a taxa shift. So we've got more gram-positive bacteria, typically in the small bowel, it seems like, and less gram-negative. And then there seems to be a taxa shift when you start to see overgrowth in the small bowel. This can happen pretty quickly when people have liver dysfunction, right? They'll see a 2-log or 1,000-fold growth in their total microbes in a fairly short amount of time in the small bowel, but as they're mapping what these microbes are, you tend to see more gram-negative bacteria starting to show up. Things like E. coli, Klebsiella pneumoniae, Proteus, other gram-negatives like Pseudomonas or aeruginosa. Those seems to be some of the dysfunctional bacteria, but there are still gram-positives there, so it's not all or nothing. There's still Staphylococcus, Streptococcus, Enterococcus faecalis, and Enterococcus faecium. They are there present as well. and they tend to be overgrown in SIBO as well. So you get both a overgrowth of certain types of gram-positive, and you end up getting a bit of a taxa shift to have more gram-negative. Right, so that seems to be characteristic in many of the studies that I've looked at in both SIBO and other conditions where SIBO is a major feature. And where are they coming from? Right, because those don't seem to be the native microbes that are generally there in a healthy small bowel. So some of the clues as to where they're coming from, like we talked about, that they are coming from the bottom, because the thing is, most of those gram-negatives are colonic bacteria, right? They're found in the colon. So, okay, it makes sense that they're naturally in the colon, they could be moving up. So I think it is, but I think that may be a secondary route. We'll talk a little bit about why that may be a secondary route. The other thing is the primary route. There's another one, which I think drives a lot of these dysbiotic microbes, and probably is occurring every single day in much more prevalence than something going up, and that's through the mouth, right? Our oral cavity. So in a couple different ways. Number one, many of these dysbiotic gram-negative bacteria are very present in the mouth. Right, so they're there all the time. So is some of these gram-positive as well. So they're there in the mouth. They're colonizing the mouth. We're swallowing spit all day long, right? We have a gastric barrier, but as you'll see, that gastric barrier is not doing what it's supposed to do in the case of SIBO. Now, the other thing is, these are all what we call fecal-oral contaminants, right? When you have contaminants in food and stuff that you're drinking and all that, you get these types of microbes that are contaminating the food. So there are lots of sources of these microbes entering into the system through the oral route, both from your mouth, the colonized microbes in the mouth, and also through fecal-oral contaminants in food, water, drinks, and so on. Right? So that is, I think, a big source of these microbes. Now, just to give you an example of that, these two bacteria, the Enterococcus faecalis and Enterococcus faecium, are really interesting because if you look at the studies, 60% of diabetic patients yielded these particular two bacteria as opposed to 6.6% in controls. So clearly, diabetics tend to have a much higher level of these microbes, right? And this is, and then if you look here, a recent study found that SIBO was present in 43% of diabetics. And this is in the oral cavity of diabetics. Right, so oral cavity of diabetics contain these two particular enterobacterums in the enterococcus, at much higher prevalence than people who are not diabetic. And diabetics also tend to have much higher levels of SIBO than non-diabetics. Right, so maybe that's one of the microbes in diabetics that actually grow in the mouth and tend to end up moving down into the small bowel and causing small intestinal bacterial overgrowth. You know, there's a really strong correlation between SIBO and insulin resistance. I'm not going to take time to go into that in great detail in this talk, but that's one of the really interesting things to think about. There's microbes that you can map that are prevalent in the mouth that can also end up growing in the small intestine, and then they're also associated with very specific conditions that are tied to small intestinal bacterial overgrowth. So why are they overgrowing? So looking at the natural protective mechanisms against this feature of microbes entering into this area where we're supposed to have pretty low levels of microbes and growing and taking shop, especially dysbiotic microbes, what are the natural mechanisms in place to protect from this? Number one, it's stomach acid, right? So the gastric barrier. We call it the gastric barrier. We say it's the first part of your immune system. It's supposed to kill stuff. Right, and it's supposed to kill stuff that we're swallowing, that it's coming into our system, and it'll also kill stuff in the stomach. It'll maintain low levels of microbes in the stomach, and then through gastric emptying, you get some acidification in the very proximal part of the small bowel before it gets neutralized by bicarbonate. All of that allows the stomach acid to maintain low levels of bacteria in this part of the digestive system. The other thing is bile secretion and the bile acid pool. Right? Bile is fascinating. It's such a fascinating compound. It does so many things, and we'll get into that a little bit more. Bile also does something, it activates something called the FXR nuclear receptor, which is found in the terminal end of the small intestine right before the bile gets reabsorbed. I'll talk about that as well. But that nuclear receptor upregulates antimicrobial compounds from the intestinal epithelium. So I'll give you a little bit more detail on that. Of course, peristalsis and the migrating motor complex, right? These are our sweeping, cleaning mechanisms. So peristalsis helps move the food along so it doesn't hang out in any one given place for too long and gets fermented or some sort of aberrant fermentation. It's like moving it along because remember, every one of these, every square inch of your digestive tract, starting in the stomach, actually in the esophagus and so on, has microbes in it. And if the food is allowed to stay a little bit too long, those microbes start to eat it and start to grow fast, right? So our system is designed in part to just keep things moving along like it's supposed to. And then the migrating motor complex kind of sweeps things out. Anything that's left there, any microbes that have grown too much, it goes on and it sweeps things out. So these are our most basic fundamental protection against SIBO and everything else that SIBO leads to, right? So I don't think that SIBO is driven by any one of these dysfunctions, right? I think SIBO is likely driven by multiple dysfunctions, at least two of the four of these things, right? So let's talk a little bit about that. First, the stomach acid, HCl production, very, very interesting mechanism. I'm not going to go super in detail, but just a couple of little things to point out on stomach acid. To begin with, it requires potassium and chloride. Of course, there are ion diffusions across a type of cellular membrane called the caniculi. And the chloride ions end up moving out, and that helps pull the proton pumps that actually pump the hydrogen ions out into this lumen of the gastric gut. This is where the chloride and the hydrogen ions meet and make HCl. Now, proton pump inhibitors, of course, inhibit this particular function. These hydrogen ion pumping actually goes against probably the strongest biological gradient in your body, right? So it has to move across and against a ionic gradient in the body, and this is the strongest one, and it requires a lot of energy to do it, and it's done by this particular player called the H plus K plus ATPase. So the production of ATP to generate this pumping of hydrogen is a major part of developing and creating your stomach acid. This is a magnesium-dependent enzyme. So with low levels of magnesium, you're going to get low functionality of this particular enzyme, low energetics. You're not going to be creating HCl at the same rate that you should be, right? And so dysfunctional mitochondria lead to this as well. This is probably the reason why stomach acid production goes down with age, right? Because if you look at the something called the mitochondrial free radical theory of aging, it shows in studies that they've done when they look at tissue biopsies of a 5-year-old versus a 90-year-old, the only difference they can find in the biopsy is a 90-year-old has more than 95% dysfunctional mitochondria. And the 5-year-old has completely 100% functioning mitochondria with high activation energy, can produce the energy that they need to function. So this ATP production that's really important to push it against the strongest gradient, so it's trying to go upstream like a salmon, and it's the strongest current in the body that it has to work against, requires a lot of energy, and that energy production is critical for this process to happen. So maintaining mitochondrial health in general, having adequate magnesium could be a really important thing. Now, in order to stimulate this in the parietal cells, you have a few stimuli. One of them is histamine. In fact, histamine is the strongest stimuli for gastric secretion, right? So think about all the antihistamines people take, right? Could that have an issue? Could that have a problem? Right, so I kind of finished the last few slides of this deck at around 3 a.m. yesterday, so I was fully intending on digging into this a little bit more and seeing if there's studies to pull up, but I totally failed. But I'm guessing, I mean, it makes sense, right? If histamine is the most important stimulator of this entire system to kick out HCl, if we're taking antihistamines all the time, there's got to be some issue with that. And the histamines that are being produced that stimulate the parietal cells to produce chlorine are the IgE-based system to kick out histamine. So, the allergic system, if you will. But we use antihistamines quite a bit. Now, acetylcholine is also another important part. And this is from the parasympathetic activity with the vagus nerve. And of course, if we're not in our parasympathetic enough, if we're in a sympathetic, we're not going to be releasing adequate amounts of acetylcholine. Studies have also showed that if you have really high histamine, but low acetylcholine, you're actually not going to be producing enough HCl. or if you have really high acetylcholine and low histamine, you're still not going to be producing enough HCl. There seems to be a really important balance between these two. You have to have adequate amounts of that. Now, of course, if you're not in your parasympathetic, that's going to cause a problem. You know, I got to sit in on the group that Dr. Marvin was in, and we were talking about this parasympathetic activation as such an important part of digestion. Right, we're eating way too fast. We're not activating the vagus nerve. You know, we're not doing the things that we should be doing to stoke this particular system, and that's probably a part of it. Another factor within this dysfunction. Gastrin, which is probably the most well-known, actually has the least effect, but it is still important as well. And then the other part is bile. Bile is really interesting. So bile has this particular composition. It's 97% water. There's a small amount of bile salts, bilirubin, of course, and then about 0.5% of fats. The main fat is cholesterol, right? So if we have inadequate cholesterol, are we not making enough bile? If we're on statins, I don't know. Again, 3 in the morning, we're supposed to dig into it. Totally fails, sorry. I will do that next time. But it brought up a question, right? So we don't know, we can't say for sure. What's really interesting is the facultative and anaerobic commensal bacteria in the small intestine, so they can metabolize bile. So bile is, of course, produced in the liver, stored and concentrated in the gallbladder, then secreted into the duodenum, or the really smart people say duodenum. So duodenum, I'll go with that because I'm pretending. It's concentrated and secreted there. And then bile is so awesome, it like sweeps all the way through the 20-something odd feet of your small intestine. It gets to the terminal end of the ileum, where before it gets reabsorbed, it upregulates that FXR receptor I talked about, and it just goes by and just gives that upregulation signal, which actually then causes the intestinal epithelium in the small bowel to produce antimicrobial peptides, or antimicrobial compounds. Right, so it's going through, it's sweeping, it's actually killing bacteria because bile is a strong antimicrobial. And then right before it gets reabsorbed through the portal vein to go back to the liver, it's giving a little high five to a receptor that goes, okay, we just clean things up, just release some extra stuff so we make sure nothing's growing too much. Right, and then it goes back to the liver, and then gets cleaned up, comes back, and gets secreted to the gallbladder, and it goes on and on. Now, what's interesting, there's 2 parts to think about, is in a single meal, the secretion of bile can be recycled like 9 or 10 times, right? So it's so important. It just keeps going around through the process of digestion, cleaning stuff up. Now, of course, you also know that it's required for the absorption of fats and fat-soluble vitamins and other important nutrients. It also does bind lipophilic toxins, takes it to the liver for clearance. So it does those things as well. But it keeps recycling to keep cleaning the system and not allow the bacteria that are there to get too excited about the food that's present and overgrow. Now, about 95% of the bile is reabsorbed every time it goes through. And about 5% of it is actually converted into something called secondary bile salts. Secondary bile salts are kind of scary stuff, right? If you ever go and Google it, you'll find all of these things about cancer, which is all true. But about 5% of it should be converted to secondary bile salts because there's a function to that, right? So that's the beauty of balance within our system. The function shows that I already talked about that the primary bile acids, the conjugated bile acids that are secreted by the liver and the gallbladder, have been shown to promote the germination of C. diff spores, while secondary bile salts inhibit the germination of C. diff spores into vegetative cells. Right, so this little 5% that's being converted there in the terminal end of the small intestine, that's actually moving through the rest of the small intestine and then entering into the large bowel. It's just enough to keep C. diff at bay. If we didn't have enough bacteria that are doing this conversion, then we would have a potential issue with C. diff overgrowth. So like there's this beautiful, elegant system to maintain low levels of microbes in this part of the digestive tract, and then just as a little bonus, there's a little conversion just to take care of these guys, right? And so decreasing levels of bile acids also start to favor gram-negative taxa shift. So that's seen in non-alcoholic fatty liver disease and so on. So you start getting lower levels of bile, you start to see this taxa shift that seems to be characteristic of SIBO. And then you also see LPS production increasing because many of these gram-negative bacteria are also producers of LPS. And I'll talk about what that tends to do in SIBO. peristalsis and the MMC, right? The other protection. So we talked about the stomach acid, HCl, bile, and what it's supposed to do. Then we've got these beautiful mechanisms of peristalsis and the migrating motor complex. We know, I think everyone would agree, in every conference I've been to where they talk about SIBO, that stasis is a major part of SIBO. But where is this stasis coming from? And then I also hear a lot of docs talking about using prokinetics, right, to get the bowels moving in. But more often than not, the prokinetics aren't really doing it. Why is that? Well, there's some clues here. If you look at some of the studies on what LPS, lipopolysaccharide, does to peristaltic activity, it really gives you a clue of how devastating it is to this really important protective mechanism. This study showed, so they were looking at pediatric small intestinal bacterial overgrowth in low-income countries. It was actually a quite large study. They found that there was a significant amount of overgrowth in countries where there's contaminated water. And of course, again, these are fecal oral bacteria that are contaminating the water. A lot of the characteristic SIBO overgrowing microbes. So they were able to study what is happening in these individuals because they're getting these huge exposure to fecal oral contaminants. And they found, they showed that it is their hypothesis that the mechanism of SIBO developed in the setting of unsanitary living conditions stems from repeated exposure to abnormal levels of LPS, so endotoxemia to a certain degree, via contaminated soil and drinking water, which abrogates the migrating motor complex, leading to luminal stasis. So this was hypothesized in this particular paper. And then there was a bunch of other studies, some of them mouse model studies, that show that in animal models, E. coli-derived LPS has been shown to decrease the frequency and strength of small intestinal contractions and eliminate the migrating motor complex, right? So shutting it down. Remember, E. coli is one of those characteristic SIBO dysbiotic overgrowing bacteria, right? And that E. coli can be coming from the bottom, but it also very likely can come from the top. Our mouth has got a good amount of E. coli in it, and if there's any food that typically are contaminated by fecal oral route, it's typically with E. coli at pretty high levels. So LPS may be doing something to stop this migrating motor complex and really create dysfunction in the peristaltic activity as well. There are a couple other studies. So this one is using mice, and they can inject the mice with LPS. And what they found was that systemic LPS and induction of the TNF-alpha, because one of the first upregulations of your innate immune system when LPS enters your circulation is TNF-alpha, right? So you've got your dendritic cells and macrophages that will start producing NF-kappa B. Then you'll get a whole cascade of inflammatory cytokines, including TNF-alpha. But they showed that LPS and TNF-alpha, when in circulation, stop gastric motility within 60 minutes of an injection. Okay, so let's think about that. If that is occurring in the human as well, you eat food, the food dumps from your stomach into your small intestine, into your duodenum, and in there you start generating LPS. And your gut is leaky. We'll talk about why the gut is leaky. And that LPS is leaking in and entering the basolateral circulation. As it's in there, the food is starting to go through the small bowel, within 60 minutes of the food being in there, all of this stuff is stopped. So now it's stopped and stuck, or at least slowed down in its journey through the small intestine. Anytime that food is not moving at the speed it's supposed to, it gives bacteria the opportunity to start to overgrow. Right, so this could possibly be a significant thing. They also showed that the effect of LPS, because what they did is they used gastrokinetic stimulants, and they were not able to turn the MMC back on. So prokinetics did nothing, because they showed that the effect of LPS and TNF-alpha acted on the brainstem in the dorsal vagal complex. So it's causing a centralized aberration of motility, right? It's not localized in the gut. It's going all the way to the brainstem where the brain and the gut are talking through the enteric nervous system, and it's stopping motility at the source where the signal is coming from, right? So prokinetics are not going to work. And LPS endotoxemia is a huge feature of anything within the dysbiotic world, right? That's another big thing. If you eat gluten, it's going to drive LPS up. So if that meal for that SIBO person has gluten in it, LPS is going to go through the roof in their blood, and it's going to get to the brainstem and stop the peristaltic activity and the migrating motor complex. Then these same researchers, they did a follow-up study, and again, they induced the inhibition of gastric motility to administration of LPS, which then stimulated TNF-alpha, as you would expect. And then when they use anti-TNF alpha compound, they were able to restore the motility in the gut using a prokinetic. So stopping that inflammatory cascade that LPS starts allows them to reactivate the migrating motor complex. Without stopping TNF alpha expression, you cannot reactivate the migrating motor complex, even with the prokinetic. So it becomes so important in something that we all talk about with SIBO, is stasis in the bowel. It becomes so important to address this inflammatory response, right? And we're not really doing it as far as I can see when I talk to people, when I talk to patients who have gone through several rounds of treatment, when I talk to practitioners who are dealing with this confusing subject, I don't hear a lot of treatment of this particular inflammatory response. Now, I also understand that patient adherence to treatment is really poor in SIBO if it doesn't almost immediately bring down the bloating, right? So that's a really difficult thing because they're looking for relief from that bloating. That's what they feel. And whatever you give them, if it doesn't alleviate the bloating, even though it may be fixing the root cause problem, they're probably not going to stick with it and they're going to be pissed at you, right? So that's your problem. That's why I don't see patients. I'm just here for the information. No, so the thing is, maybe explaining this stuff to them might help, right? So for you guys to understand this becomes so important because if you explain this to them, maybe they'll understand that, hey, we're going to fix that bloating, but that bloating is a symptom of a bigger problem that's going on, and we got to address that problem first before that bloating ever goes away. How common is this endotoxemia? Right, in healthy, normal individuals. So we're saying that LPS, if it gets in the circulatory system, it upregulates TNF alpha, it upregulates other inflammatory cytokines, and it stops the migrating motor complex, right? How common is this feature in healthy, normal individuals? Is it as common as SIBO is? Well, in our study that we published when we looked at about 100 healthy, normal college students, we found that about 55% of them had this really severe endotoxic response every time they ate food. Right, and then it peaks within 5 hours of the postprandial response. Now the thing is, the meal you ate previous peaked at 5 hours, right? Your LPS levels in the blood peaked at 5 hours. And other studies that University of North Texas has done shows that this baseline level, or this peak level, takes up to 12 hours to come back down. Right, so the meal you ate before already has loaded your system with LPS. The LPS is already in the brainstem, already shutting off the migrating motor complex. So the next meal that you eat is not really going to move. Right, so this is a really important thing that we have to think about and we have to talk about. Increased fat intake could make this worse. Right, because LPS endotoxemia is driven by higher fat intake. And when people are going on the low FODMAP diet or they're eliminating fermentable carbohydrates, they replace that with protein and fat often, right? A lot of times they will just increase their fat intake. But that could actually make the problem worse. They may not feel if they really have the fermentation, the aberrant fermentation that's causing bloating, that might feel better if they change their diet. But the root cause, the endotoxemia, is still there and still a problem and maybe getting worse, right? So a couple other things. Then we looked at part of the natural protective mechanism, stomach acid, right? So stress reduces stomach acid. H. pylori overgrowth, right? H. pylori is supposed to be in the bowel to some degree. 50% of the population, they say, is infected with H. pylori. I don't know if that term actually makes sense because I think H. pylori is actually supposed to be there at fairly low levels. Infected may mean overgrown. So I'll use the word overgrown. Zinc deficiency can definitely drive stomach acid production issues. And then, of course, the big elephant in the room is the PPIs and antacids, right? But do PPI and antacid use have anything to do with SIBO? Are there any studies on this? This was 2 a.m., so I was able to look at this. So I was still wide-eyed and bushy-tailed at that point. So there's a few studies, a few good reviews on this, and they're looking at the effects of the proton pump inhibitors. And they even quote in here several meta-analysis papers, systemic reviews, reported that patients treated with PPIs as well as, we don't care about that because that's surgery, have a higher frequency of small intestinal bacterial overgrowth compared to patients who lack those two features. They also show that at this time, PPI-induced dysbiosis is considered a type of SIBO. Right? And we know PPI use is super common. Remember, one of my theories in the beginning was all the things that are driving SIBO should be relatively common problems. right? Endotoxemia, I showed you, is relatively common. 50% of healthy normals. PPI use, you guys know the stats, is crazy. Michelle told us some scary stats on kids and PPI use, right? It's all over. And then at 2:17 a.m., I was able to find this one. Increase in incidence of small intestinal bacterial overgrowth during proton pump inhibitor therapy. They showed that SIBO was detected in 50% of patients using PPIs, 24.5% of patients with IBS, which SIBO and IBS are very, very similar, and only 6% in healthy control subjects, right? 6 and 50%. Clearly, there's a relationship there. If you're using PPIs, you're not producing HCl. That HCl is playing a role in allowing bacteria to pass through our gastric barrier from the oral route and entering into the small intestine. This is another reason why I think that the oral route is probably the more prevalent route of driving at least initial SIBO. There's a mechanism in which once you have SIBO and you have all of this dysfunction and dysbiosis in the terminal end of the small bowel, how that can actually create dysfunction in the ileocecal valve. It can certainly create dysbiosis in the cecum, especially when you have bile dysfunction and you have too much deconjugated bile, secondary bile salts moving into the cecum. It can definitely cause dysbiosis. In fact, that is associated with colorectal cancer and maybe other inflammatory bowel diseases. So PPI use, keep that in mind. Other natural protective mechanisms, of course, dysfunctions with bile. So gallbladder removal, obstruction of bile ducts, dysbiosis. Just simple dysbiosis alone can start driving dysfunction in the liver. We saw that in our study on endotoxemia and healthy normals, because what we saw is in that 30-day period where we were able to bring down LPS endotoxemia in a very significant way, we saw about a 25% reduction in triglycerides that reached statistical significance. And these are in patients that do not have elevated triglycerides. Right? These are people, the average I think was around 145, which by any standard is normal. Even that came down by 25%. Why is that? Well, because when LPS moves into the basolateral circulation, when it leaks through, it's taken to the liver. And the liver is trying to deal with it there. Right? And that is toxigenic to the liver. So that toxicity to the liver actually creates dysfunction in the liver, which can be seen through elevated triglycerides. And then also, if it gets bad enough, you can start doing liver function tests, of course. So I think liver dysfunction is another really big component to SIBO. And of course, the very common and scary liver dysfunctions are starting to crop up and increase in prevalence. And SIBO is associated with all of them. Okay, so for example, this review looked at some studies reinforce the concept that intestinal bacterial overgrowth, SIBO, plays an important role in the pathogenesis of non-alcoholic fatty liver disease. And again, this is through TNF activation, which is the same thing as LPS, which is the same thing that stops the peristaltic activity. So it can be a feedback loop, right? You could have liver dysfunction that starts and increases the issue with SIBO. SIBO then makes your liver even worse. So it's a self-perpetuating loop. Here's another larger study of 372 eligible patients. They found that out of this number of subjects, they confirmed 37.9% were positive for SIBO. Among those people that were positive for SIBO, 45.4% had non-alcoholic fatty liver disease, right? So they go hand in hand. Liver dysfunction, bile dysfunction, SIBO. SIBO makes liver even worse. Worse liver makes SIBO even worse, and so on and so forth. So that cycle keeps going on and on. And then, of course, the peristaltic, other protective mechanism, the peristaltic activity. Gastroparesis is another issue because we're not getting the dumping of the food from the stomach into the small intestine in a timely manner. If food is allowed to sit in the stomach for too long, it can ferment in the stomach. And that fermentation in the stomach, especially with stomach acid levels are low, meaning the pH is high, then it'll allow for fermentation. That creates intra-abdominal pressure, and that pressure can cause all sorts of refluxes, right? So all of this is happening, I think, in tandem, and gastroparesis, I think, is a big component of it. So in general, here's the way we think. To me, this is the way I think, and I'm not a practitioner, so you guys tell me if this makes sense. So in addition to targeting the overgrowth, so you've got companies like Biobotanical, right? They make really interesting antimicrobials that can target overgrown bacteria in the small bowel. So that becomes an important part of trying to bring down the population. But the problem is the moment you remove the antibiotic, if those other mechanisms are dysfunctional, the bacteria just grow right back, right? That's why bacteria are so awesome that way. You kill them, they come right back. You kill them, they come right back. Right? You can never kill 100% of the bacteria, really. It's always 99.9 because somebody's going to come back, right? So in addition to bringing down the aberrant growth with antimicrobials, or maybe use rifaximin if you're a prescribing doctor, we have to start by resolution of the LPS-mediated TNF-alpha stasis that's going on, or the growth is just going to keep coming back. Prokinetics won't help. So there's no real point in hammering the patient with antimicrobials and prokinetics right off the bat, which is what I typically hear and see, right, from what docs are doing. So you need to solve the leakiness in the gut. You need to solve the LPS migration in order for the prokinetics to even start working. Remember, if you bring down TNF levels, the prokinetics will start to work, right? So this should be part of the step one. Low HCl gastroparesis must be addressed. Right, there's numerous ways of upregulating HCl. I heard talks in some of the groups, and of course you've got all kinds of experts here in the room that can do that, and addressing gastroparesis as well. And I'll talk about what product we came up with to try to help with some of this. Liver support is critical, right? Because in these patients, right, not only is it maybe dysfunctional liver that started the process of SIBO is going to continue to harm their liver. Right, so if we're just hitting it with antimicrobials and prokinetics, and we're not addressing these other components, then not only are we not really resolving the root cause, we're allowing the scarier disease to get worse, right? SIBO has this cosmetic and day-to-day annoyance factor to it with this bloating. Non-alcoholic liver disease, NASH, steatosis, those are much more scary, right? Those are long-term disease with high rates of mortality. So that liver has to be supported immediately when you see a SIBO patient. You have to start them on some sort of liver protection protocol, whether it's milk thistle or whatever it is you have in your magic tool bag. To reduce the risk of comorbidities, you also have to stop mucosal damage and mucosal inflammation, because when you start digging in studies, this is a major feature of SIBO. And in fact, the dysbiosis that is present in SIBO can be started just by mucosal inflammation, right? Dr. Ravel showed that inflammation in the vaginal canal can start the dysbiosis in the vaginal canal. So inflammation in the gut one of the biggest drivers of that inflammation, wheat. Right, so your SIBO people are not going off of wheat and going 100% wheat-free, and then being really cautious with the cross-contamination of wheat, maybe using the enzymes and all that, then they're really not going to get the adequate protection to stop this process, which is part of this whole merry band of thieves. Colonic saccharolytic bacteria have to be supported, right, because what's going to happen is immediately they're going to start shrinking the number of fermentable carbohydrates that they eat, because that gives them the symptomology. That's also then not going to feed the really important saccharolytic bacteria in the colon that are producing the short-chain fatty acids for you. And you guys heard in so many studies how important butyrate is and acetate for your skin, for all these other areas. So we have to continue to support this, even though eating foods that are fermentable will be problematic for these people. So we'll talk about how we can do that in the last slide. So we created this product called MegaGuard. We've been working on colonic bacteria, what's happening in the colon, where most of the microbes are, short-chain fatty acids. We've been doing leaky gut. We've been doing inflammatory. And then we started understanding that we really have to address the stomach and the small intestine in some major way. So we put this product together, and so far I can tell you, and this is just empirical, that we're getting really great responses from SIBO people. Right, and each of these components are very well studied. We chose them because they have a significant number of clinical trials behind them. In particular, this one, the artichoke extract, is actually a prescription drug in parts of Europe. We actually had to go through all kinds of interesting hoops to get it, but it's a natural artichoke extract with a very specific ratio. It's like a 4-to-1 ratio, something or the other. Acacia knows all of that, so corner her and ask her. But it stimulates bile production and improves bile flow, and also seems to be able to naturally reduce cholesterol levels but without seeming to impact the bile. So that's an interesting mechanism. Gut guard, which is a licorice derivative, is only 75 milligrams because it's a really highly potent component of the licorice. It protects against the gastric mucosa and has clinical trials showing H. pylori control, right? Because as soon as the pH level in the stomach goes up continuously, that first thing that's going to overgrow is H. pylori. And H. pylori will maintain a higher pH in the stomach. So in order to get the pH back to normal, we have to bring down H. pylori levels. And then this ginger root extract accelerates gastric emptying. It has some bitter components in there. Bitter receptors are so important to make sure gastric emptying is happening. And then also soothes with the nauseated gut. A lot of people with SIBO report that they have a lot of nausea and things. So that really helps soothe it. So this is something you would take before the meal. So like 25 minutes before the meal, before the first bite of food, let these components go in there, let the bitter receptors get triggered, and they will actually kind of soothe that first pass of food. Then beyond that, it's kind of the go-to stuff. The megaspore to help with the LPS endotoxemia, because we have to stop that, right? And then the mega mucosa helps rebuild the mucosa, because inevitably people with SIBO have mucosal dysfunction. They have inflammation in the mucosa. They've got recruitment of innate immune cells chronically to the mucosa. You can measure something called MCP1 in SIBO subjects, and they tend to have high levels of MCP1, which is a chemokine which shows attracting inflammatory actors into the mucosa. So this becomes a really important part. So if a SIBO subject comes in, you start them with this right away to soothe the passage of food in the top part. You might start the antimicrobial right here as well, but as soon towards the end of the antimicrobial therapy, you want to start with the megaspore and the megamucosa, because we have to start alleviating the leakiness in the gut. And then the mega prebiotic is really important, and I know a lot of people get scared about prebiotics and SIBO, but these are oligosaccharides. They have long, really high degrees of polymerization. They do make it further into the large bowel. They're actually designed to make it to the distal large bowel. Specific microbes like fecal bacteria, Akkermansia, have the special enzymes to break them down. So we've actually had pretty good success with SIBO subjects tolerating this pretty well. But you go through this first with your choice of antimicrobial, perhaps the biocidin group, one of their wonderful antimicrobials, and then you start introducing this because the colonic bacteria have been suffering. Right, so this is really kind of the idea, and at the end of the day, we were trying to stoke some thinking among the group. I think this is our last slide, so that you guys can think about SIBO in a more multifactorial, multidimensional way, and understand that there are things that you need to alleviate that don't necessarily immediately alleviate the symptom, but it helps with the root cause of SIBO. So that's it, I promise. Thank you very much.